Okay. Hello, everyone. Welcome to another video about expectation maximization. Uh, EM, or expectation maximization, is a very, very useful algorithm in the statistical machine learning. It is one of the basic algorithms, uh, and anyone who is working in the domain of machine learning is expected to be familiar with this algorithm. Uh, it's very likely that you cannot find a good algorithm and good explanations or tutorial for this topic. There are a lot of equations, formula there. There are even some books, but they don't have clear motivation that why we need these expectation maximization algorithms and how we can apply it on different domains and for different tasks. If you have trouble with understanding expectation maximization, this video is going to be for you. So in a short time, I'm going to explain how expectation maximization works. Okay, so let's start. In order to understand how expectation maximization works, we need to have clear understanding of some statistical background. The first concept that we should be familiar with is probability distribution. A probability distribution is a mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. So if we have a random variable like x, and we say that x has normal distribution, it means that x gets continuous values, and its density function or its probability density function looks like this. Okay. So meaning that if you have a very short interval around value x, so you can compute the probability or the area under the bell shape of the normal distribution using this equation. Okay. When we look at this equation, pi is constant, uh, and e is the exponential function. Here we have sigma and mu. What are these parameters? Mu is actually the mean of the distribution, and sigma is the standard deviation of the distribution. We refer to these mu and sigma as the parameters of the normal distribution. Usually, some probability distributions have some parameters that if you change these parameters slightly, you totally end up with a different probability distribution. In other words, in order to define a probability distribution, we need to define these parameters. Another question is that how can we obtain the best value for these parameters? The answer is maximum likelihood estimation. So maximum likelihood estimation is the second topic that we should get familiar with. The idea is that in order to find the best value for the parameters of a distribution, we collect some examples or a set of samples, and then we use this set of samples to estimate the value of the parameters. How? Using the likelihood function. What is the likelihood function? Likelihood function is a function of theta, or the parameters of a distribution, given a set of observed examples that we collected. Okay, so we know that x is fixed, so we collected a set of samples and we fixed them, and then theta becomes a parameter of x. Okay, theta becomes a function of x, or theta becomes the variable. Our goal is to find the best value for theta. The best value for theta is the one that fits the best to the collected examples x. So in order to maximize this function or this likelihood function, so we need to compute the derivative of L with respect to theta. This is what we call derivative test. Let's look at an example. Let's say we have a a likelihood function of mu and sigma, which are the parameters of a normal distribution, and we fix the set of observations. So we go and collect a set of examples, and then we try to use these set of examples to find the best value for mu and sigma. Okay, so if you fix x in this equation, then the only variables would be mu and sigma, right? So you can easily compute the derivative of L with respect to mu and with respect to sigma. And since we want to maximize this function with respect to each parameter, we try to solve each equation. Or in another word, we try to find the best value for mu that makes this derivative equation 0. To do so, we use the set of observed data and we solve this equation. And then we observe that the best estimate for the mean of the distribution is the average of the values that we collected. And the best estimate for the standard deviation of the distribution is the standard deviation of the examples that we have observed. Okay. Now I want you to look at the binomial distribution and then tell me, or just like for yourself, you can mark the choices that are the parameters of the normal of the binomial distribution. Okay, just for those who are not familiar with binomial distribution, the main idea is that we have a binary experiment. Let's say uh, flipping a coin. So we want to check if we see the head, then we face with the success, and if we see tail, then it's not success. Okay, so it's the outcome of this experiment is binary. Now we try to run these experiments n times. Okay, so n is the number of times that we try to run this experiment. Now we want to know what is the probability of being successful k times. Okay, so we want to see what is the probability of seeing the head for k times. If k is if seeing the head would represent the success in our experiment. Okay, so we are running the experiment n times, and we want to see what is the probability of succeeding in k times, where the probability of success in one experiment is p. Okay, since it is a binary experiment, or we have binary outcome, and if the probability of success is p, then the probability of not being successful is 1 minus p. Okay? And if you success k times out of n trials, it means that for n minus k times, you failed. Okay. Now we have x, n, k, and p. We want to know which ones are the parameters. X cannot be a parameter because x is a random variable. N is a parameter because it's defined. So it's like you want to run the experiment for 10 times, 20 times. So it is a parameter. P is also a parameter that you should estimate it, and K is the outcome. It's something that you want to estimate. So N and P are the parameters of this binomial distribution. Okay, so if you answer that correctly, it means that you have a clear understanding of binomial distribution. Okay, so this is the story that we are going to do. So I'm going to give you a motivating example why we need expectation maximization, and then we start from that specific example and make it a general problem, and then we solve that general problem using EM algorithm. Then at the end, we talk about some properties and applications of EM, and then we wrap the talk or wrap this video up. Okay, let's start with the motivation. Let's assume that we are going to a country and we want to identify the gender of a person in this country based on the person's height. So the only property that we have is the person height, like X, and we want to predict the gender of the person, to which we refer by Y. So our task is to design a statistical model that takes the height of the person, like 1.67, and predicts the gender of that person. Okay. So what we want to do is that we want to have a probability distribution like P that returns the probability of Y equals 0 and Y equals 1 if we have only two genders, like two gender categories, gender category 0 and gender category 1. And we want to know what is the probability of X, what is the probability of gender category 0, given that we know the height of the person is 1.67. What is the probability of either gender category 1 given that X equals to 1.67. If we know these two probabilities, then the one that has higher value would be or would represent the gender category that we should use for X. How should we estimate each of these probabilities? So let's say we want to calculate the probability of Y equals Y given some X value, so we can easily apply Bayes' theorem. What Bayes' theorem does is that it changes the position of these Y and X. So instead of calculating probability of Y given X, we can compute the probability of X given Y times the probability of Y divided by probability of X. One important aspect is that Px doesn't affect argmax here. Why? Because Px is fixed for both of them. Here the variable is y, so in the argmax function the variable is y, and in Px we don't have any y variable, or the output of the Px doesn't depend on the y value. Okay, so this is kind of fixed, so it doesn't matter what value it takes, so we can totally ignore that. This one is the conditional normal distribution because X takes continuous value. So we can easily compute the normal distribution of X with respect to Y. And Py is also the per probability of Y, which doesn't depend on X value. So we can rewrite this equation like this, that Px doesn't have any impact. This one is the normal distribution, so we can write it like this. But since it is conditional on the value of Y, so we have a condition on the mu X given Y and sigma X given Y. And Py is also the per probability that we simply write it at there. Okay, so it's easy now. So in order to calculate the probability of Y equals 0, so we can use the normal distribution here and replace Y value with 0. So we can, if we know, if we observe a set of examples for category 0, we can compute sigma and mean. So we can do the similar thing for Py equals 1. And in order to compute these probabilities, it's obvious that we should have the parameters of the distribution. How should we obtain the parameters of the distribution, or what are the best values to represent, or what are the best values to the best values for the parameters of the normal distribution? The answer is to apply maximum likelihood estimation. In order to apply MLE, we go between people and we collect a survey. So we ask people to share their height and their gender. So we collect a set of the height of the set of people and also their corresponding gender category. Okay. Now we can easily group our examples into categories, and for each, and then we split the data set in two parts, and for each category we compute the mu and sigma, or like the mean and the standard deviation. Okay, now for a new example that or an unobserved data point that we see, uh, we can easily compute the probability of y equals 0 and y equals 1 by replacing u and sigma here. So, and since category 0 results in a higher probability, we can say that y uh, has yeah, category 0. So far so good. Um, But what is the problem? The problem is that people are not willing to share their gender with us. So if we go and ask people about their genders, apparently people face with some anxiety to release or to talk about their gender. From the statistical point of view, we are facing with a situation like this. So we collected a set of data, but the value of the gender category is hidden or latent. We know people have some genders, we know people have some genders or two categories, but we don't know each specific example belongs to which category. Okay. So what we do, okay, why is it a problem? It's a problem because we cannot group the data set in two parts and we cannot split the data set, and therefore we cannot estimate or we cannot find the best value for the parameters of the distribution. So the problem looks like this. Our goal is to find the value of the parameters of the distribution, and in order to do this, we need to collect a set of examples. But when we collect the examples, we observe that some examples or one of the variables doesn't have any value, or or its values are latent. In order to estimate the value of this variable, we need these parameters. So it seems like we got stuck in a loop. So here is the problem that we have to, here is the problem. We have to uh, actually two equations that interlock with each other. Or more or less, we are facing chicken and egg problem. Uh, so let's formulate this problem in general way. Let X be observed data. X here could be like a high dimensional feature space. In our setting, we use only height. In our example, we only use the height feature. So meaning that we only have one dimension, but in practice, actually, we have many features or many properties that represent X. And we also have Y variable that represent hidden or latent or unobserved data, depending on some parameters. Our goal is to find the likelihood function of the theta parameters given the whole set of data that we have, meaning that the joint of X and Y. How can we find the best value for theta to maximize L theta? The point is that normally we should apply maximum likelihood estimation, but we cannot apply MLE because variable y is latent here. Okay, now that we know how or where this problem happens, we can apply expectation maximization as the solution. So here is the status of the problem. So we want to estimate the value of the parameters. In order to do that, we collected a set of examples, and when we look at the examples, we see that we don't have value of y, and therefore, in order to estimate the value of y, we need the value of the parameters. Yeah, okay. Now the question is here, if we have a loop, how can we break this loop down? I want you to think about this like for 10 seconds. Let's say that you have two variables that depend on each other, and you need to somehow break these connections at some point. Uh, what do you do? So what do you break and how do you start? Okay. So similar to any other situation that that we have different resources that are dependent on each other. What we do is that we start from initializing the parameters randomly. So our goal is to find the parameters, right? So what we do is that we randomly initialize them. Now we don't have this interconnection. What we have is a set of fixed value for the parameters, and we can use them to estimate the values of the hidden variable. So let's say using these fixed parameters, we can get this estimation for the y value. And now we know how the data set looks like. So we can categorize the data set, we can split it to two parts, and use this data set to maximize the likelihood of the parameters. So we can apply MLE, or maximum likelihood estimation, to find the best value for the parameters, given that these estimations are correct. Okay, so if we run this, or if we apply MLE, we see that the value of mu changes to, or the value of these parameters changes to these numbers. Okay, we can iteratively do this. So we fix the parameters. We assume that they are the best value, or the correct value of the parameters, and then we estimate y value. And then we use y value to maximize delta. So we can iteratively go through this iteration until the model converges. This step is called E step, because we estimate the value of the hidden variable, or latent variable. And this one is the maximization step, where we assume the value of y is, or like the values that we estimated for y are correct, and we use them to maximize the likelihood of the parameters. Okay, so EM algorithm then consists of three steps. We have an initialization step that we, let's say, randomly initialize the parameters, and then we have E step that we estimate the probability of y, or just like the hidden variable, and then we have M step where we maximize the likelihood over the parameter. So we maximize the likelihood over the parameter. In our scenario, so if you compute these expectations, why do we need to compute the expectation? Because you want to maximize the likelihood over all values that y can get. So what we do is that you have the likelihood function here times the probability of the like. So if you have different y, so you can easily calculate it by this y, by a sum over this y values. Here is the main important equation. So the parameter L theta here is the variable, so you want to maximize here. But when you are estimating y, you use the O theta all parameter. Yeah. So another quiz. So what is E step in the EM algorithm? So you are going to tell me the step estimates the probability of the latent variable for each observed data, assuming that the current parameter values are correct, or it estimates the best values for parameters of the probability distribution, assuming that the current values for the latent variable are correct. Actually, the correct answer is the first one. It estimates the probability of the latent variable. Here, the second answer says that it estimates the best value of the parameters, but this is the task of the maximization step. Maximization step uses MLE to find the best value of the parameters. Okay, now the question is that when should we stop iterating? The simplest way is to define a threshold like epsilon, and then we compute the error, or like the absolute change in the value of the parameters. And if the change of the absolute change, or the absolute difference in the parameter values in different iteration is less than this threshold, then we stop iterating. Okay, let's talk about some properties and applications of EM. One property of EM is the convergence that it is important to mention here. Always remember that expectation maximization converges. So it's got expectation maximization or EM guarantees to converge. That's good. However, it always converges to local optima. And why is it important to know that it converges to local optima? Because local optima is not what we want. We ideally are looking for the global optima. And this is specifically important for high dimensional space because the number of local optima increases or is exponential in the high dimensional space. So it's very likely that the model stops in a local optima. One of the factors that affects the convergence rate and also the quality of the local mode is initialization. I said that we can start with random initialization, but based on the downstream application that we are using EM for that application, we can initialize the parameter more wisely. Although expectation maximization converges to local optima, it has a lot of nice applications in many downstream tasks, like medical image construction, data clustering, part of speech tagging. Okay, to wrap it up, as we discussed, expectation maximization is a numerical iterative algorithm to find best values of or four parameters of a probability distribution given a set of observations. So we have mainly two approaches to find the best value of the parameters in a probability distribution. The first one, or the normal one, is MLE, or maximum likelihood estimation, where we collect a set of data samples and we try to maximize the likelihood function. The other approach, but MLE doesn't work actually when we have hidden values or we are facing with unobserved data points. In such cases, we should apply expectation maximization. So if you have semi-supervised learning, or if you have clustering tasks, or if you want to do unsupervised learning, expectation maximization is a perfect, it's one of the perfect algorithms to follow. Okay, so that's good to use EM, but we should be aware of the risk of using EM, because EM converges to local optima, but still it has very effective performance for many downstream tasks. Okay, here are two references for reading about expectation maximization. Feel free to check them, and if even there is a book on expectation maximization, which could be interesting if you are really interested in this topic. Very nice algorithm for unsupervised learning, semi-supervised learning, whenever you have unobserved data or when you have latent variables, or you have missing values in your data set. Expectation maximization is the solution, or is an algorithm to find the best value for your parameters, or for the parameters of your distribution. I hope you enjoyed this video. And I hope that you got the main idea of expectation maximization. If you have any questions, feel free to write it in the comments. Don't forget to like the video and also subscribe it, and maybe share it with your friends in your classes, or just anyone who wants to quickly get familiar with expectation maximization. It's simple work. Here is Mohsen Mesgar. Until next video. See you soon.